Welcome to another video. This is Alex's World of Math, and today we're going to talk about generating functions. Specifically, we're going to focus on ordinary generating functions. So I'm going to start with the definition of an ordinary generating function. So let a of n be a function. In this case, if we use example one, it's going to be a is going to be a number of ways to flip n heads. After one coin flip. And so the OGF of any function a of n in general, it's going to be denoted by this. So you have OGF of a of n. It's going to be equal to a of 0. It's the function for a sequence for generating functions denoted by two parentheses, and then for each instance, for each n, you have a0, a1, a2, all the way up into a of infinity. Is going to be denoted by this notation. And this is also going to be equal to the sum of n equals 0 to infinity of a of n xn. And the purpose of xn is that it's like the focus of an ordinary function, ordinary generating function. And what that does is that it puts these an's as like coefficients of these x to the power of n. And so when we use like geometric sum theories, the geometric sum formula to like simplify these situations, we can try to manipulate them to get the coefficient of x to the power of n. And after we do that, we would be able to get our answer. So it's like it's a cool like combinatorics trick where you put the situation inside of this form, where you put the a of n's as coefficients of x power of n, and you try to like get this sum, and then after that you can find your answer, or whatever you want to derive by finding the coefficient of x to the power of n. And say you wanted to find the a of, like, if you wanted to find a of 3, you would just have to search for it, the coefficient of x to the power of 3. If you wanted, the general formula for a of n, you can search for the coefficient of x to the power of n. But sometimes it does take a lot of manipulating. So it's not too easy, but it's a different way to. It's a very cool way to solve combinatorics problems. And so in this case, just a practice problem. So we flip a coin one time, let a of n be the number of ways to flip n heads after one coin flip. Well, let's list this out, right? A of 0 is how many ways to flip 0 heads. It's 1, right? Because you have tails. You flip tails. That's one way to flip 0 heads. If you flip heads, that would be a of 1. Because if you flip heads in one coin flip, then you're flipping one head. And that's all the instances that I can get. You can't flip two heads within one coin flip. That would be impossible. And so you have 0, and then it keeps on going. And then it's equal to 0 for all, n is greater than 1 or greater than 2. And so this would be if we put this in the OGF notation, the parentheses notation, then we will get we will get the first a of 0 is going to be 1, second one is going to be 1, 0, 0, 0, dot dot dot. It's just going to keep on going, all these zeros after it, because you can't flip more than one head within one coin flip. And so the OGF of this would be, if we use this notation, we will get x equal to the sum of n equals 0, you know, an xn. And in this case, there's only, you know, a of 0 and a of 1 that are ones. The other ones are going to all cancel out to be 0. And so in this case, it's going to be just a of 0 x to the power of 0 plus a of 1 x1, which is just 1 plus x, right? And so that's going to be the OGF of this function. And after we find the OGF of this function, we are able to calculate some, you know, like some a of like if you wanted to find like the number of ways to flip you know, one head, that's gonna to flip one head within one coin flip, that's gonna be embedded in this coefficient of x power of 1. So that's to flip n equals to 1 heads. And so that's going to be embedded inside this OGF, which represents all the combinations. And so there's also like another cool thing is that if you want to find the number of ways to flip n heads after like 3 coin flips, say it's 3, this the OGF of that would be equal to 1 plus x to the power of 3. And this occurs for any n coins. So if you just find the you know the basis, you can multiply all of them, and that's the beauty of OGFs. If you have like a complicated situation, you can break it down to like many instances, and if you find the OGF of each instance, or each like requirement that is set upon the problem, then you can multiply all of them together and get the OGF of the entire problem, and that can help you solve for whatever you need. So if you have this, you can now like find how to the number of ways to flip like 3 heads within 3 coin flips, right? Because this is 2 power of 3, that means there's 3 times. That means it's 3 coin flips because each coin flip is represented by this. And so you have 3 coin flips. And so if we wanted to find how many ways to flip 3 heads within 3 coin flips, we would try to find the coefficient of x power of 3 within this multiplied sequence, which the only way really is to have x times x times x, which is x power of 3. That's the only instance that you're gonna get x power of 3, right? Because if you multiply 1 plus x, 1 plus x, the only way to get x squared is by multiplying these two x's. If you add another 1 plus x, the only possible way is to have the x squared times the x, and that's only one instance. So in this case, there's only one way to flip 3 heads. Only one way to flip 3 heads after 3 coin flips, and the same answer can be derived by looking at the coefficient of x power of 3 in this in the expanded form of this. And there's several things that you can do to like try to manipulate it for like harder problems. Say like you wanted to bring this to the power of 6 or 5, and then you want to find again how many ways to flip 3 heads after 5 coin flips. And so in this case, you can just use the binomial theorem that says that this can be expressed as a sum of n to 0 of to I think it's 5, and then you would have 5 choose k, or in this case choose k actually 5 choose k of x power of k x power of k. And so in this case, if we use this formula to denote this situation, this OGF, we want to find the number of ways to flip 3 heads within 5 coin flips. We need to look for the coefficient of x power of 3, and so our answer would just be when k is equal to 3. So we would have 5 choose 3. That's our answer. And that's it. And so that's the pair of OGFs. They can help you break down problems, and even seemingly like very complicated problems. Yeah, like in this case, 5 coin flips, that's a lot. And you can do this for like to any n, and it's gonna help you break down the complicated problem. And so let me give you another example. Like what if you have one, two, three, four, five, dot dot dot. How would you represent this OGF? Well, this would just be the sum of, again, it's a sum. The general formula for the OGF is going to be a sum of n to infinity of a of n xn. And in this case, a of n is just going to be, n plus one, right? Because when n is equal to zero, the a of n is going to be that. The coefficient is going to be one, and so the coefficient is always going to be n plus one. So in this case, you would have, like, if you have a of OGF of a of n is equal to this notation, then you would have, would just be represented by uh I sum of infinity n to zero of n plus one times x power n, which would just be like one x zero times x zero plus two x1 plus three x2 plus dot dot dot. You're just putting these numbers as coefficients to all the x power n, and that's all for the LGS. And yeah, say you wanted to find the number of ways to you know uh number of ways to have like uh to have a like odd number of A's within a sequence of three letters. And so you can, if you can only place A's down, you want to see how many ways to place A's down into three spots. And so and if you have like a requirement of A being like it has to be odd, how many ways to put an odd number of A's inside a sequence of three spots. Uh and that would just be like permutations, right? But if we do it generating functions, the generating function of this is gonna be, of the A sequence is gonna be limited by the number of odd, right? So zero is gonna be even, so you can't put zero. You can put one because this is gonna denote for n equals to one, and obviously we have one A that's gonna be any of these spots, right? That's gonna be three. But yeah, you're gonna have A as there's one way. Um, there's one way to have N as odd. Um, yeah, you're gonna have like if it satisfies it, then you're gonna have A as odd as one. And you're gonna have zero, you have one, and then zero, and it alternates like that. And so that's gonna be Uh, I mean, sorry, it's gonna be combinations. We're gonna counting combinations, not permutations. Because in permutations, you would have like three instead because you can do three times. But and in this case, this you can't alternate on forever because you're also limited by A cannot exceed three because you only have three spots. So you would have zero A's, one A, two A's, three A's, denoted by these, and the rest should be zeros. And so that's going to be your OGF. And so the OGF is just going to be, 0 times x0 plus 1 times x1 plus 0 times x2 plus 3, sorry, plus 1 times x to the power 3. All right, and this is going to be just x plus x3. Denoting, the number of combinations you can put with the number of A being odd and the number of A not exceeding 3. And so that's your OGF. And so now that we have practice, let's actually solve the problem. And so, all right.